Let's talk about the hidden physics of something as simple as a summer day. We're going to dive into the secret power of water. And trust me, it all starts with a question you've definitely asked yourself at the beach. You know the feeling, right? It's a scorching day, the sun is just hammering down, and the sand feels like walking on literal hot coals. But then you run into the ocean, and it's still so cool and refreshing. How is that even possible? I mean, they're both getting the exact same sunlight. Well, this isn't magic, it's just some really cool physics. So, to solve this little beach day puzzle, we first have to get super clear on two ideas that, let's be honest, we all mix up. But in physics, they are worlds apart. And that's the difference between heat and temperature. They are not the same thing. Here's an easy way to think about it. Heat is the total energy of all the little molecules jiggling around in a substance. It's about the sheer quantity of energy. So a bathtub full of lukewarm water actually has way more heat energy than a tiny glowing red spark, even though the spark is obviously much hotter. Temperature, on the other hand, is the average energy of those molecules. It's a measure of intensity, and it's what tells us which way the heat is going to flow. Right, so to put it simply, heat is the entire energy package. It's the sum total of all that molecular motion. An entire ocean, even when it feels chilly, holds a truly massive amount of heat. Temperature, though, is just measuring the average speed of those molecules. It tells us how intensely they're vibrating, and that's why the sun can pour the same amount of heat onto the sand and the sea, but they end up with wildly different temperatures. So, what's the missing piece here? The key that unlocks this whole mystery is a special property that every single substance has, its own unique ability to absorb heat. And that property is called specific heat capacity. Now, okay, that sounds super technical, but I promise the idea is simple. It's just a number that tells you how much energy you need to pump into something to make it 1 degree warmer. You can almost think of it as a substance's thermal stubbornness. Exactly. A substance with a high specific heat capacity is like a giant energy sponge. It can just soak up tons and tons of heat, and its temperature barely even budges. On the flip side, something with a low specific heat capacity, well, you give it just a little bit of energy and its temperature shoots right up. Okay, so let's take this idea and connect it right back to our beach puzzle. This is where we discover water's real-life superpower. Just take a look at this table. You can see the specific heat for things like iron or lead. They're in the hundreds. Now, look at the number for water. The difference isn't just big, it's absolutely massive. Yeah, 4,200. That number is huge. It completely dwarfs almost every other common substance. Glass, which is pretty similar to sand, is all the way down at 504. And that right there is our answer. It tells the whole story. Because water has such an insanely high specific heat capacity, the sun can shine on it all day long, and all that energy barely moves the temperature needle. The sand, though, with its low specific heat capacity, takes that exact same energy and its temperature just skyrockets. Mystery solved. But this is so much bigger than just avoiding burnt feet on a beach trip. Water's thermal stubbornness, its superpower, shapes our entire world in some really profound ways. I mean, think about it. This one property is why coastal areas have much milder climates than places inland. It's why water is the perfect coolant to keep a car engine from melting down. It can absorb so much heat. It's also why our bodies, which are mostly water, are so good at maintaining a stable temperature. It's even why a simple hot water bottle stays warm for hours. This isn't just a fun fact. It's fundamental to our technology and to life itself. So, we've figured out how much energy it takes to change water's temperature. But what happens when you pour energy in and the temperature doesn't change at all? This leads us to one last, pretty mind-bending twist. Imagine you're boiling a pot of water on the stove. It hits 100 degrees Celsius, it starts bubbling away. But if you keep that burner on high, pumping in more and more and more heat, the thermometer stays locked at 100. It just refuses to get any hotter. So, where is all that extra energy going? It has to be going somewhere, right? It's going into something we call latent heat. You can think of it as hidden energy. It isn't being used to raise the temperature. No, it's doing something way more dramatic. It's being used to change the very state of the substance, from a liquid into a gas, or from a solid into a liquid. This graph shows it perfectly. On the left, we're adding heat, and you see the temperature of the ice climbing up towards 0. But then it hits 0 degrees, and look at that. The line goes completely flat. We're still pumping heat in, but the temperature is totally stuck at 0. That's latent heat at work, right there. So what's actually happening here? That hidden heat energy isn't making the molecules vibrate any faster. Instead, it's being used for the hard work of physically breaking the rigid crystal bonds that hold the molecules together as ice, letting them finally break free and flow as liquid water. The energy gets hidden in the phase change itself. And that leaves us with one last really cool thought. It takes a huge amount of this hidden energy to unlock solid ice and turn it into liquid water. So just think about the reverse process. When water freezes on a cold night, it has to release that exact same amount of latent heat back out into its surroundings. It's like a secret warmth coming from the cold, all thanks to the amazing physics of water.
If you liked this video, then don't forget to like, comment, share, and subscribe. Thanks for watching.